Hi everybody, time for part 3, so let's take a look from our current slide. So our third part today is a third method for calculating line integrals, and this is called Green's theorem. So our setting, we have a vector field, just like before. There's my f, and we're going to define the curl of this to be the partial of the second piece with respect to x minus the partial of the first piece with respect to y. Okay, that's the curl. Note, if this is a conservative vector field, so in the previous lecture, when we found out that we had a conservative vector field, then those two things were equal. And so the curl would be equal to 0 because we have already checked to find out that those two pieces are equal, and if they're equal, then subtracting one from the other would give you a 0. If the curl is 0 everywhere, then it is also called irrotational. And if it's not rotational, it is called if it's not irrotational, it is called rotational. So this is a rotational vector field. This is the same one we looked at the very end, because I can see for this particular path the curl is not equal to 0. So it's not a gradient vector field. It does not have a potential function. It is not a conservative vector field. It is it is not a conservative vector field. It is not an irrotational vector field. It's called a rotational vector field. It doesn't have a potential function. Okay. Now here's what Green's theorem says. It says if you have a smooth vector field, which we don't need to worry about that, but it means that both of our components have continuous first derivatives. So remember the f was written as an f1i plus an f2j. So if both of those pieces were continuous and had continuous first derivatives, and if C is a simple closed curve that is piecewise smooth, which means that it only has a finite number of sharp points in it, and we already know what a closed curve is, here's what a simple closed curve is. Let me draw something that's not a simple closed curve. That's not a simple closed curve. Let me draw something that is a simple closed curve. It can look very complicated as long as it doesn't cross itself. Okay? So we've got a simple closed curve, doesn't cross itself. Okay, can be broken into a finite number of pieces with continuous derivatives, so at most a finite number of sharp points, and is oriented counterclockwise. Then the line integral can be turned into a double integral of the curl of f dA. Let's look at an example. This is the example from the previous lecture. We already know that the answer is 0, but let's try Green's theorem on it to see how that works. Okay, so when I look at this, I see that I have a simple closed curve. I see that it's oriented counterclockwise. I have only a finite number of sharp points. And I see that my function has nice continuous derivatives. Okay, because of that, I can use Green's theorem. So I can take the curl and do the double integral over the area. All right, so let's see. The curl is going to be d dy of my second function minus d dx of my first function, which is going to be a 2 minus a 2, which is a 0. So I know the answer is going to be 0, but let's talk about how we would set this up. This is a nice, beautiful semicircle, so I'm going to use polar coordinates. My r always goes from 0 to 3. And remember my dA is r dr d theta. And my theta goes from 0 to 2 pi. So even if we didn't know that the answer was going to come out to be 0 because of that 0, we could still set this up. And it's not a bad setup in this case. Not too bad at all. Okay? But we know the answer is going to be 0 because the curl is 0. Let's look at another example. Okay, so now I have negative y, x is my f. There's my f. Okay, C is the unit circle starting at 1, 0, moving counterclockwise, bang, just going around that way. So I have the entire circle in this case. So the first thing I would do when I look at these, when I try to evaluate these, I look to see how difficult they are to evaluate. And once I have a circle, I know I'm going to have some sines and cosines, so it may be a little bit difficult, but I see if it's doable. Then I check to see if I can use the fundamental line integration. Okay, so I check to see dx of my second function. Is that equal to dy of my first function? Well, that's a 1, and that's a negative 1, so no, I can't use the fundamental theorem. Fatoli, the fundamental theorem of line integration. Can't use that. So I'm stuck with either doing it by hand or doing it with Green's theorem. We could try it by hand. I don't think it's too hard by hand. Let's take a look. By hand, my parametric equations would be cosine of t, sine of t. T goes from 0 to 2 pi. So my function that I'm going to integrate is going to be negative y, so negative sine t. And then x, which is cosine t, dotted with my dr is going to be negative sine t, cosine t, dt, so I'll dot with negative sine t, cosine t, dt, evaluated from 0 to 2 pi. And when I work this out, yeah, it's not too bad. From 0 to 2 pi, the negatives will cancel when I multiply, so I'll have sine squared t plus cosine squared t dt, which is a 1. So this integral is 2 pi. That's by hand. Let's look how we would evaluate it by Green's theorem. By Green's theorem, I'm going to take the curl. I'm going to take dx of the x minus dy of the negative y. That's a 1 minus a negative 1, which is a 2. I'm going to take the double integral of 2. This is a circle, so I'm going to choose to use polar coordinates, r dr d theta. R is going from 0 to 1. Nice, easy r, because it's the unit circle. And theta goes from 0 to 2 pi. So this is not too hard to evaluate. That becomes an r squared from 0 to 1 d theta. The r squared, when I evaluate, becomes a 1 from 0 to 2 pi d theta. And so that becomes 2 pi. Same answer the other way. So this is using Green's. We did it by hand, and we found out that we could not use Fatoli. We could not use the fundamental theorem of line integration because it's not a conservative vector field. Okay, here's a quick summary of what to do. Okay, when you check the curl. Okay, if the curl is 0 everywhere, that means that F is irrotational, that it is a gradient vector field. You can use the regular method by hand, as long as it gives you an integral that's not too hard to do, or that you can easily find the parametric equations for the path. You can use the fundamental theorem in that case. So this would be where df1 dy is equal to df2 dx in this case. Additionally, or I could say the curl equals 0. Additionally, if you have a closed curve, then the line integral on that closed curve is 0. And if you do have a closed curve, then you could use Green's theorem, but why would you do that? Because you already know the answer is 0. The only people who do that are math teachers, just to show you how things work. Once you know it's a gradient vector field and you have a closed curve, you automatically know the answer is 0, so I wouldn't even bother to use Green's theorem. On the other hand, if the curl is not equal to 0, okay, then it's a rotational vector field. You can do it by hand as long as you can get your equations set up. Usually the parametric equations for the path are the hardest things, okay, but you can always do it by hand. You cannot use the fundamental theorem of line integration because the curl's not equal to 0. And additionally, if it's a closed curve, then you can use Green's theorem to calculate. Okay, that's everything in this lecture, so we will have plenty of time for questions on Tuesday. I'll talk to you later. Bye-bye.